Okay. Yeah. Dr. Benton popped in here right before you came in and said he could not make it. But he asked me to record and send him a recording because he'd want to watch it. So I'm just going to record the Zoom call. Okay. Okay. Yeah, I invited some. I asked Miss Clark about this too. I invited some friends and family to the Zoom call just to see it. I'm assuming, is that okay? Okay. I'm assuming they have to drop off once the presentations. Okay. Okay. Yeah.
If you're running it, we're going to leave your laptop. You're outside.
Yeah, yeah. I'm assuming we need to stop the recording before we start talking. So after the presentation's done, everybody jumps off. I'll stop the recording. And yeah, I can just leave the laptop since Dr. VandeWaa will be there. So that'll be fine. Okay. Just remind me to stop the recording because I don't want to forget and then later be like, what did they talk about? Hey, Brandon.
Hey,
How's it going?
it's going. I thought I was supposed to be muted, so I'm muted.
Yeah, once the presentation starts, yes. But for now we're just kind of getting everybody in. So so how's it going in Stone?
Well, Josh and I were just talking through that. This is my network admin, Josh. We were just talking through that we're actually kind of finding some peace here. We're getting
Okay.
some. We're getting to a thing where things are calming down, and we're out Monday, Tuesday, Wednesday of next week. So we're in a good spot right now.
Nice.
How are you feeling?
I'm okay. We'll see how it goes once the presentation starts. But I've run this a couple times. I ran it for our research group here at South. And I've subjected Jessica to it probably 5 times. So she's in a cybersecurity training thing at Van Cleve today, and she was like, "I'll hop on if we get out of it early." And I'm like, "Well, Jess, you've seen it like 5 times, so like you're not going to miss anything new."
That's
Um,
right.
so so that's that. Hey Chase. All right. All right. All right. And I understand that Arie lost power at LSU. So he is the third member of the committee who will be joining. So we may be a few minutes past 11:30 getting started. Just so pending them getting power back. He said he'd join from his phone if they don't get power back, so should be fine either way. Okay. Are you guys on Zoom able to see my screen share?
Yep.
Okay, awesome. Awesome. And there's Arie. Hey Arie.
Hey everybody.
Hey, have y'all got power back at LSU?
Nope, no clue what happened. So we're
Awesome.
doing it from the phone today.
Yeah. Is the weather bad?
No, something must have happened. No clue.
Oh,
So we'll see. Who
okay.
knows?
Well, it's a beautiful rainy day here in Mobile. So
Perfect.
yeah, yeah, great day for a defense. Cool, cool. Well, we've got you. I'm still waiting on Dr. Clark and Dr. McDonald to get in. And I think they'll have some administrative stuff. And I think Dr. Clark's going to email you some things. So we'll get started here in a minute. Dr. Clark just walked in, waiting on Dr. McDonald. And he's walking back out, so it's fine. I was about to throw shade at Dr. McDonald for always being late, but here we are. But well, we got 4 minutes.
Nailed it.
Nailed it. All right. And just as a general FYI, if your name is not Dr. VandeWaa, once the presentation is over, we're going to stop the recording and ask you to drop off the call so that the committee can deliberate about whether or not I should have a master's. Ooh, I think you guys are seeing the presenter mode. Or are you seeing the slideshow right now? Or are you seeing my presenter
Yeah,
view? You're seeing the
I'm seeing.
slideshow?
Yeah.
Okay. Okay, cool. Thank you. All right. Well, thanks for hanging in there. I'll be back on once everybody is in. Yes. It's a funny thing. Are you ready for something? I'm like, I think I'm ready for well, yeah, ready for tomorrow for sure. But I think I feel pretty good about it. So, so one committee member, I think while he's on Zoom from LSU, and I think everybody else is here.
Yesterday, Ken had a dissertation defense. And they were like 30.
In here, that's great. Yeah, I think the only people coming in person are.
They were standing all along the walls.
That's wild. I think it'll just be the three guys in person. Like some family friends on Zoom.
I did check it out.
Yeah, I had to web. They reject the other ones. There's no reason. You know, we have to do. I sent it to our master one day pages and she now, well, this afternoon. Thank you for that. Said it's. We'll do the same thing. Thesis template.
As usual, we're waiting on Dr. McDonald.
Class.
Yeah.
See everybody.
Oh, can you do that? Should I do that? Okay. All right.
As long as he can see us.
Yeah, I think I've got a camera on me. Well, the nice camera there is USB-A, and I don't have a dongle. So, yeah.
But the sound is working okay.
Yeah, sound's working okay. It's coming. I mean, it's just coming through the my laptop right now. I guess it could come through the speaker, but
No.
okay. No, that's fine. It should be plenty loud enough. I'll turn it up just to make sure. Where's the crowd? Yeah, I invited folks virtually. So yeah, I want a bunch of I heard the dissertation yesterday had 30 people, so we didn't want that. So okay. Okay, yeah, I can put Dr. VandeWaa up. That should be fine. Yes, and that's I already gave a general PSA to the general audience, like please drop off. So okay, well if y'all are good, I'll go ahead and get started. So first off, thanks for being here. Thanks, Dr. VandeWaa, for calling in from LSU. So today I'm defending my thesis, classifying supersonic frequencies for active acoustic exploitation, a long title to essentially say that we've created a active acoustic side channel attack that is aimed at stealing passwords from a keyboard setup. So committee members are all here: Dr. Clark, Dr. McDonald, Dr. VandeWaa. So our talk today, we'll talk a little bit about some of the research questions that we proposed in relation to looking at an attack like this, how we would go about developing an attack like this by pulling from some of the related literature that looks into acoustic side channels, both passive and active. We'll talk a little bit about some of the research questions specifically that we have and what our methodology for building this attack was, get into some results and some task correction attempts that we had to make towards the end of the project that turned it more into a proof of concept for coarse-grained finger tracking. So acoustics typically aren't a side channel that is referenced a lot in the related literature. It is mentioned in a lot of studies that talk about side channels, but typically it's overlooked a little bit because of its relatively low bandwidth to other computer operations. So whereas things like EM and power are operating in the megahertz to gigahertz frequency range, acoustics are typically operating in the hertz to kilohertz range, so much lower and much less seen to gather some kind of information. But we do see that this is possible, and we typically divide these kind of attacks into passive attacks and active attacks. Passive primarily involving listening to direct sounds, active involving injecting some kind of sound. So typically with a passive attack, it's very akin to things like eavesdropping. It's a relatively it's an old concept, right? But it's relatively new in the world of computing. We don't really start seeing these kind of acoustic side channel attacks until the turn of the millennium. In some of these older attacks, and by older I mean like around 2000, 2005, these passive attacks incorporate some kind of machine learning model. Typically, we're dealing with image-based machine learning, so we'll run these through a convolutional neural network. But essentially, what's happening is we're training our machine learning model, extracting features from training sounds. Those sounds might be individual keys, they might be entire words as they're being typed. And then we run those features against unknown attack data, which we also extract features from in order to recover some text. So we see that actually happen a lot in the passive attack space. We see it happen a little bit less in the active attack space, and we'll kind of talk about how that looks. So passive frameworks typically involve some kind of listening device in the room that's capturing operating sounds. And so those devices are typically easy to put into a situation where there are computer sounds that we want to capture, whether that's keyboard sounds, whether that's operational sounds. We exfiltrate direct data, so direct sounds made, in order to reconstruct our sensitive information. What's nice about these attacks, if you can call an attack nice, is that we don't really need any compromised access aside from the recording device. So we don't need to necessarily have access to the computer we're looking at. So just a simple diagram to show what that looks like. Part A is a computer. Part B is a smartphone. Smartphone has a microphone. And again, this is a very, very simple framework. We can insert that microphone anywhere in the environment. One of the nice things about it is we could also hide that microphone somewhere in the environment. We could put that microphone under books or under the desk. And the idea is the computer will make operational sound, or the user will type on a keyboard to make sound, and we can pick up that sound and analyze it for unique patterns that may represent individual operations. So in contrast, active frameworks typically involve injecting some sound into the environment. So rather than listening to the sounds directly made by the keyboard, we want to inject sound, observe how it bounces off objects in the environment or interacts with objects in the environment, and then analyze that data to find out what kind of movement's happening or what's happening in general. Unlike passive attacks, we typically see this taking advantage of the full spectrum of the acoustic side channel. So we really divide that into hearable frequencies and unhearable frequencies, or supersonic frequencies. Hearable frequencies being like those below roughly 15 kilohertz are sounds that we can hear if you have really good ears. But above 15 kilohertz, most people can't hear those sounds. So active attacks can actually inject sound in that supersonic framework and be pretty successful with an attack. But it does require a higher degree of compromised access. We assume that we have access to microphones to record the sound, but we also assume that we have access to speakers to inject the sound. That might be on the computer we're looking at ourselves, or it might be a different, you could do this with a Bluetooth speaker. And just to show you how this works, all on one device. This is an attack called Sonar Snoop, which we'll talk a little bit more about in the related literature, and is the basis for our attack. But essentially what's happening is we're blasting the environment with the blue frequency wave that you see there with these signals that bounce off the finger and echo in the green that you see to the microphones on the phone. And using this, you're able to capture two-dimensional movement. And so that signal is then analyzed to reconstruct some kind of movement. So our project, I wanted to reconstruct passwords typed on a laptop keyboard. So take Sonar Snoop success, which is this previous attack we had mentioned. They showed success in a two-dimensional space. We wanted to extend this to be done in a three-dimensional space. The related literature shows that this is possible, but theoretically, or it's theoretically possible, but hasn't yet been accomplished. Something very interesting that we wanted to look into. So from this, we kind of came up with three overarching research questions. The first research question asks generally, how can we combine the Sonar Snoop framework, this active attack framework, with a machine learning model that we see in the passive side of things, not so much in the active? How can we combine this in order to gather sensitive information? And then from that question, three sub-questions pop up, and those are, what specific implementation will allow the capture of user credentials? And that's usually talking about our test bed. How can we build a test bed to make this happen? We want to look at obfuscation, like how can this attack become really defensible and really hard to observe, or really hard to notice in a real world setting? And then we want to talk about defenses, because ultimately we're in the business of making sure that this kind of thing can't happen. So we want to talk about, like, okay, how can we defend against an attack like this and prevent an active acoustic side channel attack? So initially, our expected outcome, based on some of the related literature, was that we would be successful in reconstructing passwords. There are various other studies that look at active acoustic tracking as a feature, and we'll talk about finger IO and covert band more specifically in the related literature. But at a high level, they demonstrate that active acoustics can be used for both coarse-grained and fine-grained movement tracking. And also the obfuscation and defense of the signal is very practical because we are operating in that high acoustic range. So number one, people aren't going to be able to hear the sound that's injected into the environment. And number two, some of the traditional countermeasures involve like playing sound in the environment to prevent this attack from being useful. Because if you play a lot of background noise, it makes it hard for the attacker to hear anything. This kind of attack is resistant to that because it's operating in that high frequency space. And the requirement to jam in that frequency space is very expensive in both terms of power and speaker usage. So ultimately, we hypothesized that the login credentials would be successfully captured. Excuse me. So to get into some of the related literature about this, we kind of divide it into passive attacks, active features, and then active exploitation. So passive attacks, one of the first works that's cited is Asanov and Agrawal, and they look at a passive attack for keystroke recovery. They specifically combine a machine learning model to gather some passwords, or not necessarily passwords, but just typed keys, whole word. So we train on whole words, we're able to recover those keys. I included the Kocher and others paper just because I thought it was interesting that in 2011 they mentioned they do a big research project on all kinds of side channels, just surveying different side channels, EM, power, those sorts of things. And they mention acoustics as something that may not be worth worrying about because of its low bandwidth. And then 2 years later, Genkin and others were able to recover an RSA key using low bandwidth acoustics. So I thought that was very interesting. And we see a lot of projects that cite Genkin and others because they look at other system components and capturing the RSA space. And then Nana Kumar and others propose acoustic or active acoustics as a feature space. One of those is using a smartwatch to track two-dimensional motion. The other one is using smart speakers in a house to track where people are in the house. And then 2020, Ching and others weaponize it into a Sonar Snoop framework, and we'll go over that a little bit. I guess I can't hit the... So the first kind of division about this is like a cryptographic key. So we're looking at using passive acoustics to recover cryptographic keys. And really what that means is we're listening for some kind of we're looking for some kind of system response to operations that are happening. So for example, Genkin and others listened to coil whine or like the operating sounds of a computer as it was encrypting and decrypting using RSA operations. And they were able to, over a longer period of time, and that's pretty common in the space, over a longer period of time, reconstruct a key. So essentially, the presence of abnormal or ramped up sound indicates ones, and the absence of that indicates zero. So we're able to pretty easily communicate binary data. I gotta stop doing that. So essentially what this looks like in practice is, so Gary and others looked at system fans and DeGuittard, Bassano and others looked at printers. So you can see that the system fans, as they're encrypting, as the fans rev up and as there's more volume coming off of those fans, we represent that holistically as a one. And as they relax, we represent that holistically as a zero. If you look at the chart on the left, you can see that that's happening over the course of about a minute. We're getting just 7 bits. So this is much slower than we see in other side channels, but we do show that it's possible. DeGuittard Bassano does something very similar with a printer. And what's really unique about the printer attack is even like that figure would make it seem like we saw some kind of weird data on a sheet of paper. But what that actually is as the document was printing, the printer made abnormal sounds for specific lines, and those represented ones when captured by a microphone. So what's nice about this is when the user prints a document, unless they're really listening to the operating sounds of a printer, the document that's printed is relatively benign. So it's a pretty defensible attack that may go unnoticed, especially in like an office setting where users either aren't walking by the printer or aren't really noticing what's going on with the operating sounds of that printer. So then we move into the keystroke capturing space, and this is where it starts getting a little more relevant to our research specifically. Asanov and Agrawal first look at this kind of attack, recovering passwords from acoustic emanations, specifically dealing with passive sounds. So they're looking directly at the sounds made by keys. They do use machine learning in order to classify these words as they're being typed. They assume that we're dealing with non-random passwords or non-random words because they don't train on individual keys. They train on entire words. But they do use a classification model. They also introduce another approach that we incorporate into our own research, which is different typing styles. So they did traditional typing, which is what you would expect, finger on F, finger on J. But they also did hunt and peck typing, which is like we're looking at the keyboard, we're searching for a key. It's a little bit slower, it's a little bit less efficient. But they wanted to see how that differentiated it, and they were able to show that they could recover passwords pretty successfully in both cases. So something that comes up a lot in this space, in this passive space that we're kind of looking to move into active, is aural deep learning. And essentially, it's image-based machine learning. It's image-based classification. So we take a raw audio wave, we convert it into a spectrogram, which is just a frequency map of audio frequencies over time. We run it through a convolutional neural network to extract features, run those through a linear classifier to extract our labels. So in the case of Asanov and Agrawal, those labels would be the word the word dog, whatever. In the case of our research, those would be individual keys. We'll get into how that looks every time. I'm going to do that every time. Sorry, y'all. So for the development of active acoustics, we do see a shift in the related literature circa 2016 with Nanda Kumar and others. And again, they proposed their papers, Finger IO and Covert Band, they proposed as features. Finger IO looked specifically at, okay, can we inject active acoustics or high frequency into the environment and record the reverberations off your fingers as they move to track two-dimensional motion. So if the user draws a J, the computer performs some action. Covert Band looked at more coarse grain. They looked at can we look at smart speakers in a house and can we determine what room people are in? And they were able to actually show that by using active acoustics in a coarse grain fashion, they could find out what room people were in within a house. This is very interesting. It is a significant improvement over passive acoustic attacks, mostly because if there's a lot of background noise, this isn't as effective, right? Because we'll show a little bit about how that looks, but this is a fairly defensible signal because it's operating in that supersonic range. It's gonna be every time, y'all. I'm sorry. So sonar indicates physical location, and really at the end of the day, this is what this is. This is a miniaturized sonar system using relatively low acoustic frequencies for sonar, because sonar is really, really high frequencies, which makes it really useful for a large space. You think about submarines, you're trying to map out a large space. But when you're talking about mapping out a smaller space, like a keyboard, these relatively low frequencies that are still too high for humans to hear are more appropriate. And basically what we do is we create these echo profiles. And when we start talking about machine learning, these are essentially the features that we're pulling out. So the red line represents sound at 1 second, the black line represents sound at 2 seconds, and that would manifest in a spectrogram. As you're looking at that echo profile, you can see the difference in signals and know that a finger is moving about 35 centimeters away from the microphone. So this is really nice for acoustic tracking, and Sonar Snoop takes it, weaponizes it, and says, okay, how can we use this to track finger motion as we're just drawing Android unlock patterns? Typically, you need 2 microphones to capture movement in a 2-dimensional space. You have 1 microphone tracking an x-axis, you have 1 microphone tracking a y-axis. The challenges in generalizing it to a laptop system is you really need a 3rd microphone, because you need to record a z-axis. You need to know when the finger's coming up off the keys and moving around on the keyboards as well. Didn't do it that time. So the Sonar Snoop finger framework essentially took the Finger IO and Covert Band Tech and weaponized it and said, okay, we're going to inject OFDM signals, orthogonal frequency division multiplexing signals, in the 18 to 20 kilohertz range. And those OFDM signals are typically used in wireless networking, and they're used for their resilience. They're very robust signals that bounce off objects, and essentially the fact that you get a cellular signal inside a building is thanks to these OFDM signals that are being so resilient, bouncing off objects. We sample, so we inject that in kind of a small space. And the idea is that it bounces off fingers. We set our sample rate in the microphone to 48 kilohertz. So Nyquist's theorem says that whatever your sample rate is, you can capture frequencies, real frequencies at half of that. So by setting it to 48 kilohertz, they can capture real frequencies up to 24. And essentially, they're playing the sound, they're drawing Android unlock patterns on a phone, and they're analyzing the reverberated sound to reconstruct those unlock patterns. And they were able to actually show that they could either reconstruct the pattern outright or significantly reduce the number of guesses needed. And by significantly reduce the number of guesses, basically what that means is the phones will lock you out after 5 or 6 attempts to draw the passcode. If we can limit the guess pool to about 5 or 6 and get in the phone with one of those, they considered that a success, and they were able to do that. So the proposed defenses in the related literature, we see that traditional countermeasures are becoming less effective because we're moving to that active space. And by traditional countermeasures, I mean like acoustic signal jamming. Now, that's not to say that signal jamming in the side channel is impossible. It is possible to inject supersonic sound, but it's not a perfect solution, because typically we have 2 issues that come up. One is power. It takes a lot of power to inject sound. When I was running this on my laptop, my battery drained really quickly, so I had to keep it plugged in at all times. So there is a large amount of power. The second issue is that speakers aren't really meant to be run in that high frequency for that large amount of time. So there's an argument that you could build speakers to withstand that. You could eliminate speakers entirely. You could eliminate microphones entirely. But number one, eliminating speakers and microphones isn't really a practical suggestion. Users need those features. And number 2 is, even if we did do that, that doesn't affect the systems that are already in production. So how do we help those systems? So there really is a lack of widely applicable defensive proposals to deal with this problem. So to get into our methodology a little bit, our goal was to generalize the Sonar Snoop attack to be used against a laptop system. So we're looking, rather than a 2-dimensional space as seen in Sonar Snoop, we want to construct this attack in a three-dimensional space. So we developed a machine learning model to classify supersonic keystrokes based on their spectrograms. And then we want to infer labels on that unseen data, similar to how those attacks looked previously. And then as the last part of this, we wanted to discover various obfuscation techniques that we could use to hide our attack. And then we wanted to look at potential defensive techniques we could use to beat our attack. So our research approach, we basically applied the Sonar Snoop model to a laptop computer. And rather than use two microphones, we used three microphones. Like Sonar Snoop, our attack was limited to a single computer, and we'll talk a little bit about how that looked. But the microphones collected the training and testing data, which was the reverberated OFDM signals shown as spectrograms. And we use that training data to train a convolutional neural network deep learning model. Each key was used as a label. So we had 94 labels total for each possible key that could be entered. And then we inferred labels on unseen oral data by recording passwords and inferring label on those individual keys as we type. So we made a couple of assumptions for this framework. Number one was we assumed that we have speakers capable of supersonic production. And this is common. And we did show that, like we went through and made sure that we could see, like, hey, this is we can actually produce supersonic production or supersonic signals with our setup. We assume that we have the ability to inject OFDM signals or some kind of compromised access to speakers, which we would need in this kind of attack. We also assume that we have access to at least 3 different recording devices because the related literature hypothesized that doing this kind of attack in a 3-dimensional space would require an additional microphone. But one of our goals was to see if we could do this with fewer. Okay. Let's talk a little bit about like why doesn't background noise matter? Because I kind of alluded to that and talked about that specifically. Like, why don't we care? So this is just a sample spectrogram recorded in Audacity of me typing the University of South Alabama on this laptop recorded with an iPhone. And if you look at the spectrogram on the left, you can see where those you can see each of those keys, and you see that into the side channel, and you think, well, it seems like the direct signals do matter. But you can actually do a frequency analysis and look at sound frequency over hertz, or excuse me, you can look at sound level over frequency over hertz. And what it shows is if you look at about the 10 kilohertz range, that's the main frequency. And then around 15 kilohertz, you get these overtones or these reverberations of the acoustic signal through the side channel. And you notice that around 15 kilohertz, it's pretty strong. But then around 18 kilohertz, you're still seeing that, but it's much weaker. So you notice that the background noise, you could have all the background noise in the world. If it's not being jammed in the side channel, we're still able to observe other frequencies in that range. And this shows 2 things. It shows what the features look like, and it also shows that our speakers are capable of producing supersonic frequencies. So OFDM signals use carriers. And if you look really closely at those signals, you can kind of see the individual carriers as they play through the space. You can also see me typing a key right before 3 seconds. And the idea is the signal that you see is finger movement. It's not the actual sound of the key being typed. It's my finger moving and pressing whatever key I pressed. And the idea is as that signal interacts with the carriers, that's the feature that we would be able to extract and analyze in the spectrogram. So just to give you a diagram of how that attack looks and how training looks, we blast OFDM signals into the environment, and then you can see that in the orange waves there. Those bounce off fingers seen in the blue waves and are collected by a microphone. Those signals are used to train our model. We run it through our deep learning pipeline that we showed earlier, and then we output some kind of model weight. And this is an early model that we ran. We were actually able to do a little bit better than this, but that just shows kind of a preliminary idea of how training worked. So our model was sourced from various audio deep learning resources available online. We were able to put this together really quickly using various Python scripts. We used a 5-layer convolutional neural network. The full model uses 150 samples per label. So and we'll talk about why it's 150. It was originally 600, but we ultimately decided to proceed only with the combined microphones rather than the individuals. But there were 94 labels total. We developed our model using just a subset of that, so only the lowercase letters. And for the full model, it takes about an hour to run this at home on a PC using a 3080 Ti leveraging CUDA. Okay. So this shows the experimental setup for data collection, and this essentially shows we used a program called Logic Pro. It's Mac specific, but you could use Audacity to do the same thing. It shows an iPhone or an iPad used to collect oral data on either side. We originally were going to use Android tablets, but those actually had a frequency rate capped at 16K, so we wouldn't have been able to catch anything in our side channel. You'll notice that we're sampling at 44.1 kilohertz, and that's not exactly the 48 kilohertz we sampled in Sonar Snoop. The reason for that was the iPhone and the iPad are actually locked to 44.1 kilohertz. So thanks, Apple. But we had to stay in that space. But 44.1 is more than sufficient to capture 18 to 20 kilohertz. So we were okay with that. So the laptop speakers emit the OFDM signal. The OFDM signal, as it bounces off fingers typing, is recorded by the microphones. And then we can analyze that data in training. And then for inference, we developed a remote application and database to store the entered passwords so that we could go back and look at those to make sure that they were about what we wanted. So for training and testing data collection, we did a single key typed in various styles. We typed these in 2-second intervals and did a data collection of 5 minutes per key. So if you split that up, it's 150 samples per label. When you don't include the other microphones, we only included the aggregate signal. So the spectrogram constructed from the iPad, the iPhone, and the top microphone. We collected 94 keys total, and that is 26 lowercase letters, 26 uppercase letters. So some of these letters were shift plus a key, so a little bit more movement there. And we pre-processed those files to remove some of the noise. So we pretty much eliminated the entire sonic range and highlighted the interest area between 18 to 20 kilohertz. So humans hear audio logarithmically rather than linearly. It's much easier for us to hear frequencies, for us to differentiate frequencies 100 to 200 hertz than it is 10,000, 100, 10,200 hertz. So typically when we're talking about audio deep learning problem, we are talking about problems in the oral space. You think about your voice assistants, those kind of things. They're trained using image-based recognition this way, but we want to use what's called a Mel frequency spectrogram because it's a logarithmic scale. For our problem, that doesn't work because what ends up happening, as you can see in the figure, we crush everything that we care about. So we need to use a linear spectrogram and we need to zoom in on the side channel, the 18 to 20 kilohertz range that we care about. So in order to collect our inference data, we typed, the setup was similar to what we used for training. It was exactly the same. And we typed passwords into a field, submit it to a database. And the reason behind the database is so that when we're inferring on label, or we can just make sure that the passwords were entered correctly if something doesn't come back correctly or come back expected. We created audio recording files for each 12-character password. And we use different typing methods to enter those passwords a total of 6 times. Now, this is the part of the project where we did get to a little bit of task correction. So unfortunately, we only were able to look at that first password in common.txt, that auto discover. But these are just passwords selected from 2 lists of words. Common.txt, I think, is used in web servers, and then Rocky.txt, which is a common word list that you would find in like Kali Linux or some kind of penetration testing. And you can kind of see the idea for these was to get more complicated as they go down, and to really test our ability to infer. But unfortunately, we did run into some problems with this, so we had to do some task correction and convert just a little bit. But this just shows the database. I did develop like a very, very simple first in, first out database. The idea was capture the password, store them in the database, and then after we infer, if something doesn't come back as we expected, we can go back and check it against the database to make sure there wasn't a typo. That was the basic idea of that. So moving into our results, holistically, our training went very well. We were very happy with the model's ability to classify the labels directly. We initially used a training and testing set, although later on, as we refined the model, we did add a validation set, and those came back really well. We were very happy with the overall accuracy, which sat at about 85 to 90%. In validation and in testing. So we're pretty happy about that, but it struggled to infer labels on data collected in different sessions. So something that immediately popped out to us was, okay, we need to redo this a little bit and maybe normalize the data. But we'll talk about that a little bit more towards the end of the results section. We did end up doing a subset to do a proof of concept for coarse-grained finger and hand tracking. So to construct our model, one of the issues that we ran into and that required us to construct a model from scratch was the fact that pre-trained models are almost exclusively trained at 16 kilohertz. And you think about it, it makes sense. Normally, for audio deep learning problems, we're talking about speech and we're talking about oral range. So 16 kilohertz can capture up to 8 kilohertz, and that's where we're speaking. Nobody's really speaking higher than 8 kilohertz. It's also practical because these file sizes are smaller. One of the things that was challenging about collecting data sampled at 44.1 kilohertz was all of our files tended to be pretty large. So I actually had to take advantage of like an external hard drive just to hold everything for training. Even if you get rid of things in the acoustic side or in the audible side channel, those files are still large. So we opted to train the model from scratch. There was some publicly available logic for deep learning in the audio or in the hearable range. So I just modified that to be usable for the supersonic range. Initially, we did a 66-33% data split between training and testing. And later on, as we were refining that, we added a validation set, did 70-15-15 split. As we move into these models that we trained to develop it, we trained it only on, at first, the lowercase subset, so 26 labels, 150 samples per label. Initially, we were using a MEL spectrogram, and then we moved to a zoom linear spectrogram. We also used a histogram to highlight some of the features in the spectrogram. Essentially, how this is going to look are our odd-numbered models were used on the entire data set. So the holistic microphone recordings and the individual, like the iPhone recording, the iPad, the MKE, those microphones were included as well. And what you see in this was we used a MEL spectrogram here. So initially, you see that we have much more accuracy in training with only the combined microphones. So the individual microphones show like a lot of noise that throws off our training. But again, keep in mind, we're using our MEL spectrogram here. So we're actually crushing the data that we actually care about. So in the next iteration, models 3 and 4, we used a linear spectrogram, and immediately things get much better. Now, this is before we added any early stopping logic. So this is definitely an overfit model, but we can see that we converge relatively quickly, but we are much more accurate when we're only using that combined data. We had a test set accuracy of roughly 90% versus 70%. So we kept that in for models 5 and 6, where we're using the histogram to highlight features, and this converged much more quickly. So we did end up going with model 6. Keep in mind that this was only trained on 26 labels on the lowercase alphabet. We used that model to train our full model on 96 labels. We added some early stopping logic. So this converged pretty quickly. We stopped training right before 50 epochs. And we had a set accuracy and validation and testing of about 85%. So that's we were pretty okay with how this looked. And we pulled a confusion matrix, and we see that we felt that training went very well based on the results shown in that confusion matrix. So to show some of those results by class, we can kind of see that the sides of the keyboard get a lot better with the training. You see that we have high accuracy. This is test accuracy, by the way, but we have high accuracy in our on the sides of the keyboard, 0, 2, 3, 6, 8, and some of those uppercase letters. So it really likes when we are typing 2 keys at once. But we had some of the weaker accuracy in the middle of the keyboard, so right below that MKE microphone. So we thought that was interesting. Then we went back and inferred labels. So I collected the Auto Discover password set. And when we went back to infer, we got predicted labels, not auto discover, not strictly auto discover. So this didn't even come back close. So that was concerning. So the first time this ran back, we had to kind of step back and say, okay, what can we do to control the environment? So we did a couple of things based on this. We pretty much added our validation set to training to make sure that that was as effective as possible. We also went back and we collected, we collected our data in one session rather than collecting across multiple sessions. So I went back and did just a lowercase subset of data and then trained on that. We still had these same problems. So we really had to step back and say, okay, how can we figure out what's going on here? Let's look at the data directly. So we did a spectrogram investigation. We looked at spectrograms for just like the letter A. I created a Python script that went through and aggregated all of these spectrograms on top of each other. So on the left, you see the spectrograms for training. On the right, you see the spectrograms for inference. And right away, we see some differences, right? There's a lot more activity going on in the 0 to 20 frequency bands in training than there is in inference. There's also some activity going on between the 50 and 60 timeframes in those higher frequency bands versus inference. And essentially what that boils down to is this is an image-based deep learning problem. The model is looking at images and it's running it against images and inference and saying, does this look the same? And if it does, let's assign it this label. And if it doesn't, let's not. So what we pulled from this was these really don't look the same. And so we said, okay, there's probably some kind of background variable, likely excess motion, that's causing these spectrograms to look different. So let's go back and collect a subset of lowercase letters as a proof of concept. So rather than fine-grained finger tracking, which is the ability to track a finger for each key, let's do a more coarse-grained finger tracking and look at the ability to track fingers for regions of the keyboard. So we selected the labels, just 6 labels, A, D, E, I, M, P, and those represent distinct regions of the keyboard. And so we tried training on that. We did 2 tests on this. The first test that we did, we collected 150 samples per label, just as we were doing before for all 6 of our labels. And then we did 5 sets of 10 samples on the A key. And the way we trained this was we ran, okay, we're going to train on just the training set, just 150 labels. Then we're going to train on training set plus A inference set 1. Then we're going to train on training set plus inference set 2, and then so on and so forth. And we used our models to only infer on the A key. We didn't look at B, E, I, M, or P. But we got some encouraging results from just this. So if you look at the chart, or if you look at the table, like not including any of those inference sets results in 0% accuracy, which was expected based on our previous results. As soon as we included that first inference set, all of this data collected in the same session, by the way. As soon as we included that first inference set, we jump up drastically. Set 1 is 100%. That's expected because it's included in training. But set 2 through 5 jump up. Same thing for 1 through 2. Set 3 through 5 jump up, and then so on and so forth. And if you look at set 1 through 4, you can see that set 5, which was not included in training, is now hitting 100%. And just for fun, we included 1 through 5 to make sure. And obviously, that's all going to come back 100% because it's all included in training. But those results were encouraging. But the problem was it's possible that we were biasing this model now to return A, right? We didn't try this on other labels, but based on the results of this test, we said, okay, well, let's train our model on more labels. So what we did was we did another round of data collection. Again, this all in the same session, and we collected 3 sets of 150 samples per label. So we we trained on round 1 with 150 samples per label, round 2, 300, round 3, 450. And then we used the models to infer labels on all 6 of the key. And what we found was the accuracy generally improved. There were some outliers, but overall things looked pretty good. With model 1, the outliers were E and P, which we found pretty interesting because P was on the side of the keyboard, but E's towards ish the middle. So we thought that was interesting. But with model 2, as soon as we include more labels, everything jumps up with the exception of E and P, which go down slightly, which may account for the fact that there are other labels that are doing better. And then model 3, things generally go up with the exception of the A and the B key. But generally by model 3, our inference looks a lot better. And so I also collected AVEIMP in the same session, and that consistently improved. So based on these results, we felt pretty strongly that essentially we need a lot more data to train with this. And the challenging part of collecting data for this project is it all has to be done in real time. It took to collect this data set in one session took about 4 hours, and that doesn't include the overhead of having to go through, pre-process it, run it through the model, those sorts of things, which took several more hours, several days actually. So, you can imagine the time overhead for collecting 450 samples for 96 labels or 94 labels. So to conclude, we find that deep learning is effective for image-based classification in training. We're very successful at that. We're very happy with how that model looked. But the model is weak in terms of inferring labels on unseen data, which is kind of the whole point, right? So we want to make sure, in the future, there is potential future work in building up that data set, reducing the number of microphones needed, or applying a transformer model. And that's something that popped up in the related literature a little bit, something that might be able to look at more nuanced data and either reconstruct with fewer microphones or fewer labels. I thought that was interesting. But to address our research question specifically, we find that the Sonar Soup framework can be generalized. We figured out how to do that with our setup, but inference still remains an issue. So with the machine learning model, we start to run into issues, but we did have success training a model by applying a successfully constructed test bed that captured motion in 3 dimensions. To address robustness, a robust model that's trained with a lot of data could allow success in a real world situation, assuming it's sufficiently trained. And that would be our big takeaway there. As far as defensive recommendation, they remained largely unchanged. We would still recommend jamming in the side channel if possible, and limiting speaker usage, especially in environments like SCIFs. We don't probably want to avoid having speakers on those systems completely if we can. Another thing that beats this model in its current state is excess motion. So an attack like this right now would be majorly thrown off if, as you're typing, you're moving around a lot. And we found that in our experimentation as well. So we make that recommendation. So there is future work available, more data collection. We've gone over that real-time data collection is a challenge. But if anybody really likes sitting in a room typing a single key for 8 hours, this is the project for them. There's possible future work in refining pre-existing models. Again, the problem with that for this project is those models are mostly trained on 16 kilohertz data. If we could find a way to apply those models to this data set, they're trained with a lot of data. This could be very useful. But again, we couldn't find a way to do that without really crushing our data. There are audio spectrogram transformer models out there. They're trained at 16 kilohertz, but if we could build one that was trained for 44.1 kilohertz or 48 kilohertz, that could also potentially be a very effective project that may be able to take advantage of the fact that we want to use less microphones and we have fewer samples per label. We may also look into whole word classification, although this probably isn't going to be effective for like randomized passwords. But if you want to show it more as a proof of concept that this kind of finger tracking is possible, this may be an effective approach to take. Okay. With that, are there any questions?
Already have.
Any questions online, Dr. VandeWaa?
No, I'm all right for right now.
Okay. Dr. Clark, Dr. McDonald, Dr. Chapman. Anything?
One thing I was thinking about, so
Yeah.
you're only OLED emphasis
Mhm.
coming from the speakers.
Yes.
You can get better results if it came from a different source than the actual speakers.
I think the results would be different, not necessarily better. The advantage of playing the OFDM signals on the computer itself, especially like a laptop system where you've got speakers on both sides, is you're kind of equally injecting that OFDM signal into the environment. And that might have something to do with why the sound was stronger on one side of the keyboard versus in the middle. I think based on how the model's trained currently, I think if you injected OFDM, so like if you had a Bluetooth speaker next to the computer, I think that like with no other improvements to the model, I think that your label inference would be stronger on those keys that were on the side of the speaker that was injecting the signal and would probably be weaker on the other side. Does that make sense? Just based on where the microphone or the speakers are at. So I think that would be the effect there. Yeah, and that might be well. Another approach that could be taken is if you had two speakers that you're injecting on either side, that would work. That's essentially happening on the laptop, but it would work if it was on an external device. And something that may help with accuracy, maybe somehow having a speaker on top, like overhead, the same way you have an overhead mic. So that might also be something that improves the accuracy of this model.
So I think the next step is to ask our.
We got a few people online, so thank you all for coming. If y'all could drop off,
Except for Dr.
yeah, unless your name is Dr. VandeWaa, we'd really appreciate it. Thanks for checking it out. We really appreciate it.
And if you could put Dr. VandeWaa out there.
Yeah, I will. All right, he's on. Let me stop. Yeah, don't record the. All right, thanks, Dr. Chapman. All right, let me stop our